This is the pre-lab lecture for the Measuring the Melting Points of Compounds and Mixtures laboratory in Organic Chemistry 1. The objective of this lab is to measure the melting point of pure compounds as well as mixtures and observe the difference between these two. And then finally, in the last part of the lab, you will be assigned an unknown and asked to use the mixture melting point technique in order to identify the unknown. Just as a reminder, remember that melting points, which may be abbreviated MP throughout the slides, isn't really one single number, it's actually a range. So to properly record this, when crystals first begin to liquefy in this experiment, that's the low point of your melting point range. And once the entire sample is liquid, that is the higher value within your range. And you will need to report both of these to correctly let me and your TA know what your melting point range of the sample is. Remember that the presence of soluble impurities will lower the expected melting point. This kind of harkens back to general chemistry knowledge and how these impurities impact intermolecular forces. So if you have an impurity in a sample, you will have a lower than anticipated melting point for the sample. Additionally, you'll have a broadened melting point range. So instead of a 1 to 2 degrees C range for a pure compound, an impure compound might have a melting point range of 5 to 8 degrees C. In the graph below, you see an image of two compounds and their melting points plotted. We have a compound X and a compound Y. Their melting points are recorded as pure, so X melts at 150, Y melts at 146. When they are mixed together, you see that they have the impact of lowering each other's melting point, depending upon what the ratio of the compound X to compound Y is. That varies the impact on the mixture or impure sample melting point. Here's a better look at this illustration, and the thing to focus on for this slide is whenever you have a mixture of two compounds, there is something called a eutectic melting point and a eutectic composition. So for our example of solid X and solid Y, the eutectic melting point is the lowest melting point for a mixture of two compounds, and for these two, that is going to be 130 degrees C. Right here. And we know that that's the eutectic melting point because that's where effectively we have our lowest temperature recorded for a mixture of solid X and solid Y. The composition at that lowest melting point is considered the eutectic composition. And so that's where both components of the mixture are in equilibrium with the liquid and the mixture is fully melted. So for our theoretical example of solid X and solid Y, X's mass percent in the sample is 40%, Y's mass percent is 60%. That combination yields the lowest possible melting point for any combination of X and Y, and that temperature again is 130 degrees. You will be asked to make a similar plot for two compounds, two known compounds that we will be giving you in lab, and you will have to identify the eutectic temperature as well as the eutectic composition for those two compounds. Keep in mind, eutectic composition is not consistent. It varies upon what these two solids are. So it could be 50%, 50%, 50%. It could be 60-40. It just varies depending upon what mixture you're dealing with. So I mentioned earlier that you'll be using the mixture melting point technique to identify unknowns. Obviously, we should all recognize that melting points are physical constants, and we can make identifications of unknowns based off the melting point of a compound. However, a lot of compounds have very similar melting points, so you have to do a little bit of digging. You can't just assume that the melting point is one definition. While it can be, that could also point to several different compounds. In order to kind of do this extra work, as I've said, and figure out and kind of confirm that you really do have the compound you think you do, we use what we call a mixture melting point. Effectively, what that's doing is mixing a small amount of a known compound with a known with a known melting point with your unknown. Ideally, this small amount of known compound has a melting point very similar to what your unknown is. Perhaps it's something that you think your unknown compound might be. If the melting point, once you mix these two compounds up, you take a melting point of the mixture. If the melting point of the mixture is the same as that of the known compound, then your unknown compound is likely the same as the unknown. Effectively, there's no impurity in that mixture or what you thought was a mixture, therefore the melting point doesn't change. However, if the melting point for your mixture decreases or if that range broadens, that's an indication that there's an impurity, and there's a good chance that your known and your unknown are different compounds, and you would need to go back to the drawing board and identify another known compound to compare your unknown with. Here we see figure 2 from the lab book. This is a nice flow chart, kind of helping you to map out how to determine an unknown from the mixture melting point technique. Here we're told that you have an unknown with a melting point between 133 and 135, and you have identified that it could be benzoin or tranexamic acid, both of which have melting points in a similar range. So first you mix your unknown with benzoin, and you do the melting point technique to analyze it. If the melting point is much larger than 133 degrees C, then your unknown is not going to be benzoin, okay? If your melting point of that mixture ends up between 135 and 137, which is, if you refer back to the top, the melting point of benzoin and also within your unknown melting point range, then your unknown would be identified as benzoin. If your melting point ends up much lower than 133 degrees C, so you've had a lowering of the melting point due to an impurity, i.e. your unknown, then you go to your second option, your other potential unknown, which was tranexamic acid. Mix the unknown with the tranexamic acid, and you should see, hopefully, that your melting point for this sample is 133 to 134 C, a very small, narrow melting point range, identifying your unknown positively as tranexamic acid. Of course, there's always the chance that there's another compound that it could be in a similar melting point range. Therefore, if you do have a melting point that has a much lower melting point than tranexamic acid, you have to go back to the drawing board and revisit other possible compounds. So things to remember when using your mixture melting point technique to verify purity. Melting point range of 5 degrees C or more indicates that your compound is impure. So you know that the two things that you've mixed together do not share an identity. Pure compounds should have a narrow range, like we've said before. That's somewhere between 1 and 2 degrees C. And remember that you can always go back and purify a compound to narrow that range further. While we're not doing that in this lab, we will be able to use this technique of purification and reanalyzing melting points to verify that we have purified a sample in later labs. Likewise, once a compound's been purified, not only should the range of the melting point be smaller, but the melting point itself should increase because you've gotten rid of those impurities that are doing the melting point depression or causing the melting point depression.